Hello, Matt here from chemistrystudent.com. In this video, we're going to look at proton NMR spectroscopy. We're going to talk about what spin-spin coupling is, how peak splitting occurs in high-resolution NMR spectroscopy, and the use of the n+1 rule with examples given. Before we talk in detail about peak splitting and spin-spin coupling, it is essential you are comfortable with the general theory of proton NMR spectroscopy and how it works. This has been covered in much more detail in a separate video. Check the links in the description below. As a quick recap for this video, however, proton NMR spectroscopy is a technique used to analyze compounds in organic chemistry. Spectra are produced that give information about the number of unique hydrogen environments in a molecule based on a number of peaks in the spectra, how these environments may be arranged based on the chemical shifts of these peaks, and the ratio of the number of hydrogen atoms in each environment based on the ratio of areas under each peak in the spectra. In proton NMR spectroscopy, the nucleus of a hydrogen atom, a proton, has its magnetic field flipped against the direction of an externally applied magnetic field, by its spin also being flipped. Energy is needed to do this and comes from radio waves. When this happens, resonance is said to have occurred. Depending on the specific environment of a hydrogen atom, different amounts of energy are needed to flip the spin of its proton, meaning hydrogen atoms in different environments in a molecule absorb different frequencies of radio waves as their protons are made to resonate. The number of different frequencies of radio waves absorbed by a sample will be the same as the number of unique hydrogen environments in the molecule. Recap done? Let's go! High-resolution proton NMR spectroscopy can give very useful information about the number of hydrogen atoms bonded to adjacent, non-equivalent carbon atoms in a molecule. By adjacent, non-equivalent carbon atoms, we mean carbon atoms that are bonded to the same carbon atom a hydrogen atom is bonded to, adjacent, that aren't bonded to the same atoms or group as that carbon, non-equivalent. It sounds a lot more confusing than it is. For example, with the molecule ethanol, the two hydrogens bonded to the first carbon, the CH2OH group, are bonded to a carbon that is bonded to another carbon atom. This other carbon atom will be described as an adjacent carbon. This adjacent carbon atom is bonded to 3 hydrogen atoms and is therefore bonded to different atoms and groups to the first, meaning it is non-equivalent. It isn't the same type. As a result, we would say the 2 hydrogen atoms bonded to the first carbon in ethanol are bonded to a carbon that is bonded to an adjacent non-equivalent carbon atom that has 3 hydrogen atoms in its environment. Without trying to make things too confusing here, if a hydrogen atom is bonded to a carbon that is itself bonded to an adjacent non-equivalent carbon atom that has hydrogen atoms bonded to it, these hydrogen atoms can affect the energy required to flip the spin of the proton in the original hydrogen atom. They can make it slightly easier or harder to flip its spin. This is described as spin-spin coupling. The protons in each of the hydrogen atoms bonded to adjacent non-equivalent carbon atoms interact together, and this creates a weak magnetic field. This weak magnetic field can either be in the same direction as the external magnetic field being used in the NMR process, or it can go against the direction of this external magnetic field. In the first case, more energy is then needed to flip the spin of the proton in the original hydrogen. And in the second case, less energy is needed to flip the spin of the proton. This now means 2 possible frequencies can be absorbed by the same proton environment. One upfield, nearer the 0 ppm TMS peak, and one slightly further away, downfield. Now, rather than the original hydrogen environment giving just one large peak in the NMR spectra, this peak now gets split into two smaller peaks that are very close together. This is described as peak splitting. For example, imagine the molecule ethanol. The hydrogen environment on carbon-2 has 3 hydrogen atoms in. This would give a large peak in an NMR spectra. However, the carbon atom these hydrogen atoms are bonded to is also bonded to another carbon atom that is itself bonded to another hydrogen atom. This other carbon atom is next door to the first carbon, meaning it is adjacent. And as it is bonded to different atoms and groups, a single hydrogen and double bonded to an oxygen, it is non-equivalent. The proton in the single hydrogen atom on this adjacent non-equivalent carbon atom has its own magnetic field that can either go with the external magnetic field direction, making it slightly harder to then flip the spin of the hydrogen protons on the second carbon, or it can go against the external magnetic field, making it slightly easier to flip their spin. There is equal probability of each happening, meaning both situations will occur. This now means that rather than there being one single peak for the 3 hydrogens in the CH3 environment, there are actually 2 smaller peaks. The difference between the 2 smaller peaks is absolutely tiny, as the effect of the magnetic field of neighbouring protons is very small, meaning these peaks are still very close together. This splitting can only be seen on a spectra if a high resolution is used. Hence, we only observe peak splitting in high-resolution NMR spectroscopy. The really interesting and useful thing is that different numbers of hydrogen atoms bonded to adjacent non-equivalent carbon atoms can cause peaks for other hydrogen atom environments to be split differently. Specifically, the main peak for a given environment will be split into n+1 smaller peaks. This is called the n+1 rule, where n is the number of protons, or hydrogen atoms, bonded to adjacent non-equivalent carbon atoms. If n equals 0, then there is only one peak, called a singlet. If n equals 1, then there are 2 peaks, called a doublet. If n equals 2, then there are 3 peaks, called a triplet. And if n equals 3, then there are 4 peaks, called a quartet. When n is more than 3, the n+1 rule still stands. However, the peaks are often described as multiplets and can start to look quite confusing. For example, in a molecule of ethanol, there are 3 unique hydrogen or proton environments. The first, the hydrogen in the OH group. The second, the 2 hydrogens bonded to the carbon that is bonded to the OH group, and the third, the 3 hydrogens bonded to the carbon that is bonded to the first carbon. This would give 3 peaks in a standard proton NMR spectra, 1 for each hydrogen environment. However, the peak splitting for each of these will be different, and we can use the n+1 rule to predict the peak splitting that we would expect to see. The first hydrogen isn't bonded to a carbon, meaning there are no adjacent carbons bonded to it either. As a result, n must be 0. Remember, n+1 equals number of peaks, meaning 0 + 1 is 1 peak, a singlet. No peak splitting has occurred. The second hydrogen environment, the CH2 group, does have an adjacent non-equivalent carbon atom that it is bonded to, and this carbon has 3 hydrogens bonded to it, meaning here n equals 3. Again, n+1 is the number of times the peak gets split. 3 + 1 is 4, a quartet. The final hydrogen environment, the CH3 group, has an adjacent non-equivalent carbon atom that it is bonded to, the CH2 group carbon. This carbon has 2 hydrogens bonded to it, meaning n equals 2. 2 + 1 is 3, meaning the peak gets split into 3, a triplet. Really important to notice here, however, that the number of times a peak gets split isn't based on the number of hydrogen atoms in that environment. It's based solely on the number of hydrogens bonded to adjacent non-equivalent carbon atoms. You gain no information about the number of hydrogen atoms in the environment the peaks are referring to, without using the ratio of areas under each peak in the spectra. For example, for ethanol, the ratio of areas under each peak will be 1 to 2 to 3, telling us that there is 1 hydrogen in the first environment, 2 in the second, and 3 in the third. So, to summarize, Proton NMR spectroscopy gives useful information about the number of unique hydrogen environments in a given compound. High-resolution NMR spectroscopy gives further information and can be used to help identify how many protons, or hydrogen atoms, are bonded to non-equivalent carbon atoms in a molecule. This information is obtained from peak splitting. The protons on adjacent non-equivalent carbon atoms can either make it slightly easier or harder to flip the spin of a given proton in a molecule, splitting its peak in an NMR spectra. The number of times a peak is split is based on the number of protons on adjacent non-equivalent carbon atoms, and complex splitting patterns can form, given an n+1 rule, where n is the number of hydrogens bonded to adjacent non-equivalent carbon atoms. If n equals 0, then there is only 1 peak, called a singlet. If n equals 1, then there are 2 peaks, called a doublet. If n equals 2, then there are 3 peaks, called a triplet. And if n equals 3, then there are 4 peaks, called a quartet. When n is more than 3, the n+1 rule still stands, however the peaks are often described as multiplets. It is important to remember that peak splitting tells us information about the number of hydrogen environments on adjacent non-equivalent carbon atoms. It isn't based on the actual environment of the peak. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.